The universe has quite a number of stars. That's an understatement, actually. Our galaxy alone contains over 200 billion of them. The one we're familiar with, otherwise known as the Sun, has been shining brightly for over 5 billion years, and will continue to do so for about an equal amount of time. However, like all stars, our Sun will eventually die one day. After this happens, life will no longer be possible on Earth, but it's still fascinating to think what happens when a star like our Sun reaches the end of its life, and what's left behind afterwards. When the Sun dies, it will gradually expand into its red giant phase, eventually shedding its outer layers into space and becoming a white dwarf. This is basically the leftover core from the star, and it is a very dense object which gradually cools down over an indefinite period of time. However, stars which are many times more massive than our Sun will suffer a much different fate. A large star, such as Betelgeuse, an extremely massive star located about 640 light-years away from Earth, will literally obliterate itself in a terrific explosion known as a supernova. This catastrophic event will likely leave behind an object known as a neutron star, which is an extremely dense object with some very interesting characteristics and properties. This program is designed to focus mainly on neutron stars, and will take a deeper look into how they form, what they're made of, and the extreme conditions associated with them. Many scientists from around the world study these objects, and one of them is David Kaplan, an assistant professor in the Department of Physics at the University of Wisconsin-Milwaukee.
A neutron star is what's left over after a star explodes. So a star like the Sun will go on happily converting hydrogen into helium and releasing a little bit of energy. And that little bit of energy is what makes life on Earth possible. And it will happily do this for about 10 billion years, and it's somewhere around halfway through that now. Our Sun is sort of an average-sized star. If you started instead with a star that was maybe 10 times as massive as the Sun, it would go through all that nuclear fuel much more quickly. Instead of taking 10 billion years, it will maybe take 10 million years. So it'll go 1,000 times faster. Moreover, it will do much more extreme things to that fuel. Instead of just converting hydrogen to helium, and then our Sun will eventually convert a little bit of that to heavier elements, a more massive star will go from hydrogen to helium to carbon to oxygen, all the way up until its center is made of iron. And once its center is made of iron, you can't get any more energy out of it by nuclear reactions. So iron is the most stable you can get. So while that's happening, the star is still losing a whole lot of energy because it's still shining. And in fact, it's much brighter than the Sun. So it's maybe 1,000 or even more times brighter than the Sun. So it's losing its energy much, much more quickly. And so if you have something that's losing energy, but it can't manufacture any more energy in the center, eventually it will collapse. And that collapse is what we see as a supernova. So the star basically says, my God, I just can't keep up this whole charade anymore. And the central layers fall down onto each other. We don't really understand completely how all of that works. But what's left over in the center is a neutron star, and then a whole bunch of hot gas flying off at a speed of about 10,000 kilometers a second. So that hot gas flying off we can eventually see as a supernova remnant. And then the neutron star is what was the very core of that star that has been squeezed together. So it's been squeezed so intensely that every little trick to save some space is possible. So you know, if you have a pair of shoes and a box of shoes and you need to squeeze them into a closet, you can put your shoes in the box and you'll save a bit of room. And neutron stars go through a similar exercise. Most matter is made, we know, of protons and electrons and neutrons. And those all take up room. Turns out that if you squeeze protons and electrons together hard enough, you can make neutrons. So instead of having a proton plus an electron, you get one neutron. And that will save you some space. And so for neutron stars, this has happened to a very, very large degree, so that the vast majority of the matter in the star has just become a big ball of neutrons. There are little bits of other things in there you need for various reasons, and the outside is made of more or less normal matter. But for the most part, you can think of it as a big ball of neutrons.
So now that we know how neutron stars are formed and what they're composed of, let's explore some of their characteristics and other properties. Even though neutron stars are considered exotic celestial objects, they do have some things in common with the stars from which they evolved, such as rotating about their axes. But something interesting happens when a spinning object becomes smaller, and you may have experienced something similar on an ice rink, even though this phenomenon occurs on a much larger scale.
So most things in the universe rotate. The Earth rotates once a day. The sun rotates about once a month. And so most other stars will rotate. And when you have something rotating, it has what we know as angular momentum. And when the star collapses in on itself, this angular momentum has to go somewhere. So if you have an ice skater who's spinning around really quickly, if this ice skater brings his or her hands in, they'll spin even more quickly. That's because you're conserving angular momentum. And so for something that's smaller, you have to spin more quickly. And the same exact thing happens for neutron stars. When the star is really big, when it's the size of the sun, it might spin once a month. But once it collapses down to something the size of a neutron star, which is maybe only 10 miles across, something where you're squeezing the entire mass of the sun into something the size of a small city, it has to spin really fast. There's a theoretical limit to how quickly a neutron star can spin. This comes from a number of different things. First of all, the outer bits of a neutron star have to be moving more slowly than the speed of light. Second, the outer bits of a neutron star have to be part of the neutron star itself. If you're spinning around quickly with some weights in your hand, at some point you're not going to be strong enough to hold those weights as you spin more and more quickly, and you're going to let them go and they're going to fly off and hit somebody. And for a neutron star, the same thing happens. As it spins more and more quickly, the bits on the outside are having more and more of an urge to fly off. And when it spins quickly enough, the material on the outside would fly off and it would break apart. We think this is something around maybe 1,000 times a second or maybe 2,000 times a second. We're not actually sure of the details because no neutron star has been seen spinning that quickly, and the theoretical calculations are rather complicated. They explore areas of physics that we can't really understand with normal experiments on the Earth. And so the only way to understand them is to find a neutron star that's spinning faster than what you thought it could.
As you can probably imagine, an object with the mass of the sun packed into the size of a small city, which also may be capable of rotating up to 2,000 times a second, carries along some other extreme characteristics. Next, we'll learn just how extreme a neutron star really is, including their incredible density, immense gravity, intense magnetic field, actual spin rate, and what would happen if you were to visit one of these small but deadly objects.
The star that is going to become a neutron star is typically somewhere between 10 and 20 times the mass of the sun. Figuring out just what those limits are is actually very interesting. We don't know them to any great precision right now. But you start out with something that's, as I said, 10 or 20 times the mass of the sun, and the neutron star that's left over, we think they're pretty tightly grouped around 1.5 times the mass of the sun. So a lot of that leftover mass is flung out as really quickly moving gas. And this is the material that we can see when we see supernovae in other galaxies. It is also how the heavier elements get out into the universe. We ourselves are made up of a lot of its water, which is hydrogen and oxygen, but we also have things like iron in our blood. And for the most part, those things were made in supernova explosions that happened billions of years ago. So when all this matter is flung out really quickly, it enriches the rest of the gas in the galaxy with all these heavier elements. So the neutron star that's formed is typically about 10 or so miles in radius and has something like 1.5 times the mass of the sun packed into that. So neutron stars are the densest objects that we know of. If a star were not quite massive enough to explode and leave a neutron star at the center, it would leave behind a white dwarf, which is pretty dense. It's something like 1,000,000 times denser than water. So there you're squeezing something like the mass of the sun into something the size of the Earth. So that's still pretty extreme, but neutron stars are a whole lot more extreme. You're taking something the mass of the sun and squeezing it into the size of Milwaukee. So you end up with something that's roughly 100 trillion times the density of water. So 1 teaspoon is about 1 trillion kilograms, and a cube 300 meters on a side would have roughly the same mass as the Earth. When you squeeze all this mass into such a small volume, it means that the gravity gets really, really strong. So gravity controls how much we weigh. We all have a certain amount of mass. If we were in space, we would have 0 weight. On the Earth, we know how much we weigh. On something like the Moon, our weight would be somewhere in the middle. On the Moon, it's about 1/6 of what we weigh on Earth. On neutron stars, the gravity is about 100 billion times higher than on Earth. Now, your bones wouldn't be able to support you. In fact, you would just be a puddle on the ground. Neutron stars also typically have a magnetic field. The Earth has a magnetic field, which is why we can use compasses to figure out where north is. So on neutron stars, it's a whole lot bigger. As with everything, on neutron stars, things are more extreme than they are on Earth. So a neutron star has a magnetic field that's about 1 trillion times the magnetic field of the Earth. Now, not only would this point your compass quite easily, it would erase your credit cards from about 20,000 miles away and kill you from about 100 miles away. Neutron stars spin very quickly when they're born. We don't know exactly what limits that, but we know that they can spin as quickly as 100 times a second. Later in their life, they can spin either more quickly or more slowly than that. So we know that neutron stars can spin faster than a kitchen blender, 700 times a second. So if you can imagine being on something where you're just a puddle on the surface, where you've squeezed the mass of the sun into something the size of Milwaukee, have a magnetic field that will kill you from 100 miles away, and you're spinning 700 times a second. That's what it's like on a neutron star.
As you can see by now, neutron stars are some pretty extreme objects, and you would probably never want to be anywhere near one. So far, we've learned quite a bit about neutron stars in general, but let's venture in a slightly different direction and discuss a special type of neutron star known as a pulsar. They are just as extreme as normal neutron stars, but they have a feature which allows them to, well, outshine the competition.
So a pulsar is a particular kind of neutron star. Almost 1,000 years ago, a star exploded. And this explosion was actually seen and recorded by people on the Earth. It's present in a number of historical records. We can now see the neutron star left over by this explosion. We call it the Crab pulsar because it's at the center of the Crab Nebula, which is a cloud of gas that is glowing because of the energy given off by the pulsar at the center. So if you think of a lighthouse, once every time the lighthouse goes around, you see a little flash of light. The same thing applies for a pulsar. You get a beam of light coming out of the magnetic field of that neutron star. And if it so happens that that beam of light crosses past the Earth, every time it spins around, we see a little blip. This blip is usually radio waves, but for some pulsars, the little blip can be optical light, just like you'd see with your eyes, or even X-rays or gamma rays. So those blips come once every time the neutron star spins. Therefore, they come as fast as 700 times a second.
Now that we've seen the lighthouses of the universe, let's explore one of the different scenarios under which a pulsar can exist, such as a binary system with a normal star. This type of system can actually end up making a pulsar spin more rapidly as it ages, which is a pretty interesting process. It involves a transfer of matter, And since there are some extreme forces involved, you can bet that this is anything but an ordinary scenario.
So about half of the stars that we know about in the sky are in binary systems, where there are two stars that orbit around each other. Now, if one of those stars happens to be massive enough, it will have a supernova explosion and could very well leave behind a pulsar. The other star has a good chance of surviving the supernova explosion, and if that happens, then it will be orbiting around a pulsar, or they'll be orbiting around each other. And we know of a good number of these. We know of a few dozen such examples, where you have a pulsar and a normal star orbiting around each other. Now this is fine because the normal star will in general live a reasonably long time and will sort of go about its life pretty happily. But eventually this normal star may itself use up all of its fuel. And when that happens, it will expand. It will become a red giant. Our sun will do this in about 5 billion years. Other stars will do it more quickly. When it becomes big enough, the gravity from the neutron star becomes stronger than the gravity from the other star, and it sucks some of that matter from the other star onto the neutron star. So it ends up hitting the surface of the neutron star at a speed that's a good fraction of the speed of light, and this releases a whole lot of energy. So if you drop a rock on the Earth, it will hit the ground with a bit of a bang. And that's basically taking the energy and releasing it as a bit of a bang. If you do this on a neutron star, you release a whole lot of energy in the form of X-rays. And it can actually release more energy per kilogram of matter than a nuclear bomb. So when this happens, these neutron stars release a whole lot of energy as X-rays, and we can see them as X-ray pulsars. So when the material is falling onto the surface of the neutron star, it releases a whole lot of energy, but it also does other things. It also brings with it some angular momentum. So the angular momentum controls how quickly the neutron star spins. When you're taking the angular momentum from this material and adding it to the neutron star, it will make the neutron star spin more and more quickly. So in general, as a neutron star ages, it spins more and more slowly. It's getting tired, it's using up its energy. And if you take a normal pulsar and start it spinning something like the crab at 30 times a second, it will end up spinning once every 10 seconds after about 10 million years. But if it happens to be in a binary system with a normal star, some of the material from that star can make it spin more and more quickly, and it will reinvigorate it. We call these recycled pulsars. So they will spin more and more quickly, and we'll end up going for something that spins once every 10 seconds to something that spins almost 1,000 times a second. So because they spin 1,000 times a second, they spin almost once every millisecond, and therefore we call them millisecond pulsars. But a more technical term is recycled pulsar.
So we've covered regular neutron stars and various types of pulsars in binary systems. In addition to learning about these objects, physicists have also used them to validate certain aspects of Einstein's theory of general relativity. Many of his predictions have not only been confirmed by experiments performed here on Earth, but also by the observation of various objects in space and the behavior they exhibit when interacting with other objects. One particular binary star system which was studied gave astronomers a chance to validate yet another one of Einstein's predictions, and also led to the discovery of an even more impressive binary system. This discovery is turning out to be quite valuable for physicists around the world.
A binary with a pulsar in a star that's a little bit less massive than the star that became the pulsar, it will eventually run out of its nuclear fuel and it will explode in a supernova explosion. This will happen so that you'll have two pulsars or two neutron stars in the same binary system orbiting around each other. And we know of a few dozen of these systems in the galaxy. The first one was discovered with the Arecibo telescope in Puerto Rico by Russell Hulse and Joe Taylor. And what they found out was that by measuring it very, very precisely over decades, they were able to show that the size of the orbit was very gradually getting smaller. Now, the fact that it's getting smaller turned out to be really, really interesting. This is because one of the predictions of Einstein's theory of general relativity is that when you have a binary system, the binary system should be losing energy and angular momentum to gravitational waves. These are little ripples in the very fabric of space-time itself. They carry energy away from the orbit, and when they carry away this energy, they make the orbit smaller. And Hulse and Taylor, along with other collaborators, were able to show that the orbit was getting smaller at exactly the rate predicted by general relativity. And for this, they won the 1993 Nobel Prize in Physics. Now, that was a pretty impressive discovery, but since then, we've discovered an even more impressive binary system. The binary that Hulse and Taylor studied was one where you only see one pulsar. The other object we know was a neutron star, but that's only because we know that there's nothing else that it could be. We don't see it. But this decade, we discovered a double pulsar system. This is a binary where we can see pulses from both of the objects in it. One of them is a pretty normal pulsar that spins once every 2.5 seconds or so. The other one has been recycled so that it spins more quickly, about 50 times a second. And we can see pulses from both of these objects. This enables us to confirm different aspects of Einstein's theory of general relativity and to go even a whole lot further. So it's proving to be a very, very fruitful laboratory for understanding what happens when you have pulsars and where all the energy and angular momentum go.
Pulsars may give physicists another avenue for testing other aspects of Einstein's theory of general relativity. Scientists have been trying to measure the influence of gravitational waves on space-time itself for years. To do this, physicists have come up with a clever solution to the problem by using the accurate timekeeping nature of pulsars themselves.
Pulsars are among the most stable clocks that we know of. In fact, some of the best pulsars are as good as the best clocks on the Earth. We don't know which is worse because it's hard to tell. The pulsars are so accurate that we can take measurements on Monday and look 2 years later and find that the pulses are coming exactly when we predict they should. So this opens up some really interesting avenues to do sensitive tests of the material between us and the pulsar. So these pulsars are thousands of light years away. And between us and them is a whole lot of nothing. Now, people have hypothesized that the Big Bang and very massive black holes at the centers of galaxies should be giving off gravitational waves, a lot like the gravitational waves that came from the Hulse-Taylor binary. But instead of happening once every 8 hours, these gravitational waves will have periods of tens of years. So very, very slow waves. And what it does is it makes the space-time between us and the pulsar stretch in different directions. So we are hopeful that within the next decade or so, we'll be able to use pulsars to detect this stretching. What we do is we look at different pulsars in different parts of the sky. And if we can see that a pulsar over to one side has pulses coming a little bit earlier than we expect, while a pulsar over to the other side has pulses coming a little bit later than we expect, we can deduce, if we're careful enough and we've eliminated all other sources of error, that those differences are coming from the stretching of the space-time itself due to gravitational waves. Some of these may be left over from the Big Bang. Some of them may be from very massive black holes and galaxies far away. But in either case, it's really interesting.
Good.
In conclusion, it appears neutron stars and pulsars are not only extreme celestial objects, but also provide physicists with valuable information for their research. As more of these stars are discovered, the greater the chance they will be able to assist us in unlocking even more secrets of our mysterious universe. If you're interested in learning more about David's research, please visit the website at the bottom of your screen. More information about neutron stars can be found at nasa.gov and at many other websites around the internet. I'm Bruce Hicklin. Thanks for watching.